Imagine you're riding on a brand new, sleek, high-speed train, just zipping across the countryside, hundreds of miles an hour. Or maybe flip that. Maybe you're the brilliant engineer who actually designed its critical braking system. What's the absolute number one thing you want to know about that system? Or really, any critical system? It's reliability, isn't it? Will it work flawlessly, exactly when you need it most? Will those brakes bite every single time? Now, here's the real challenge, though. How do you prove something is reliable, truly reliable, before it's out there, before it's carrying thousands of people or running essential infrastructure for years? How do you test it without, waiting decades for things to naturally wear out? Or worse, risking lives in the real world? This isn't just some abstract technical question, right? It's fundamentally about trust. It's about safety. And it's about protecting huge investments. It's really a bedrock principle for any critical system. Today, we're going to take a deep dive into something absolutely crucial for, I think, every engineer out there, especially if you're working in safety-critical fields like, say, railway systems. We're talking about reliability demonstration tests, RDTs. We're going to unpack the often hidden risks that come with these tests. We'll explore some surprisingly smart ways to design them. And we'll uncover why some seemingly simple methods can actually be, quite dangerous if you don't fully grasp the statistics underneath. Okay, let's get into it.
Yeah, and it's definitely more than just crunching numbers, isn't it? We're really exploring these fundamental trade-offs the engineers, project managers, even procurement folks face constantly. It's that really tricky balance between having genuine confidence in how a system performs,
right,
managing the often significant cost of doing thorough testing, and also meeting those, often really aggressive timelines to get a product out the door into service. Every single decision rule, every parameter you choose in these reliability tests, it carries an inherent risk. You just can't avoid it. There's risk for the producer, the company making the system. And just as critically, there's risk for the consumer, the organization buying it and running it. Understanding these risks, how they intertwine, it's not just academic. It's absolutely vital for responsible engineering, for making properly informed decisions. And ultimately, it's about building the safe, dependable infrastructure we all rely on every single day.
Okay, so let's start by navigating these risks. These, as you said, often hidden risks. Here's the core dilemma, right? The inevitable catch. You want to prove your product, your system is solid, it's reliable. But you just can't test it forever. You can't run a train's braking system for, say, 50 years in a lab to see if it actually lasts 50 years, or expose new signal system to every possible weather event for a decade. It's just not feasible. So what do? We have to use a limited period of observation. You run a test for a certain amount of time, or maybe on a certain number of units, and then you have to make a pretty pivotal decision based just on those limited observations. And this immediate reliance on, limited data, this snapshot in time, it automatically introduces uncertainty. It has to. It's a bit like trying to judge a world-class chef's overall skill, their consistency, just by tasting one single dish they made. That one dish. It might be incredible, a total masterpiece. But statistically, it could also be a fluke, a lucky one-off that doesn't really reflect their average work. Or, the other way around, that dish might have a tiny flaw, something minor. And it makes you think, maybe this chef isn't so great, even if their usual standard is actually sky high. This uncertainty in reliability testing, it really boils down to two critical types of risk. And they affect different sides of the deal. So first, there's what we call the producer's risk. Statistically, it's known as a type I error. This is when a product is actually reliable, it meets the specs, it's genuinely robust, performs just like it's supposed to. But your limited test results, maybe just due to pure chance or some weird, unrepeatable thing happening during the test, they make it look bad. And so it gets unfairly rejected by the customer. Imagine you're that train manufacturer. You've poured years, millions maybe, into R&D for this fantastic new signal system. Genuinely top tier, built to last. But just because of some rare, unlucky fluke, maybe an unexpected power surge during the test, caused a temporary glitch. Nothing systemic.
Right, or just a couple of minor, unrelated issues happen to pop up in that short test window.
Exactly. And because of that, your system fails the RDT. Even though it's actually good, maybe even excellent, you lose the big contract, your company faces serious financial losses, all that R&D cost, missed revenue, and your reputation takes a hit. That's producer's risk. It's frustrating, it's costly, and it can feel incredibly unfair if you've made a quality product. Okay, so that's one side. Then on the flip side, and arguably even more concerning from a public safety view, is the consumer's risk, or a type 2 error. This is the opposite problem. The product isn't reliable enough. It doesn't actually meet the required safety or performance standards. It's got underlying flaws, but
maybe by sheer luck during the test, or maybe just because the test period was too short to really stress it properly and reveal those flaws, the limited test results look good. So it gets accepted. And think about a railway operator here, the consumer. They're buying a new critical component, say a vital track switch controller, or maybe an onboard diagnostic system. If this thing passes the RDT but is actually failure prone in the real world, that's a direct, serious threat down the line.
Absolutely. A failure could mean dangerous delays, huge operational disruptions costing millions, not to mention emergency repairs, and in the worst case, catastrophic accidents, injuries, or even worse.
Exactly. The consumer unknowingly buys a lemon, thinking they got the gold standard.
Yeah.
And the consequences, they can be devastating, way beyond just money. So the main goal, the whole point of a well-designed RDT procedure, is to try and make both these risks, producer's risk and consumer's risk, acceptable.
Right.
Acceptable to both parties. It's about finding that sweet spot where neither side feels like they're taking on an unreasonable amount of risk. And of course, you got to do this while juggling the real-world constraints, the budget for testing, the cost of the items, the often intense pressure to get things done on time. It is absolutely a delicate balancing act. A statistical tightrope walk, you could say, where the stakes are just incredibly high.
Precisely. And what's really interesting here, and maybe a bit alarming sometimes, is how often contracts, especially for big infrastructure projects or critical railway parts, still have these clauses that are, well, overly simplistic, often dangerously so. I mean, I've seen countless RFPs, calls for tenders, with something like this. The mean time to failure, the MTTF, calculated as total observation time divided by number of failures, TN, must be at least 100,000 hours over a 1-year period. Seems straightforward, doesn't it? Run it for a year, count the failures, do the math. What could possibly go wrong?
Yeah, sounds simple enough. T divided by N.
But the fundamental issue is that the MTTF estimate you get from that simple TN calculation, it can be wildly inaccurate. It's a really unreliable snapshot, especially if the observation period is relatively short compared to the true MTTF. It's a bit like trying to guess someone's average lifespan by just watching them for one day. You might see them trip, or maybe they don't, but that tells you almost nothing about their overall health or how long they'll actually live, does it?
Oh, really? No.
The true value of the system's reliability, its actual underlying MTTF, that's what really matters. Not just one potentially misleading estimate from limited data. And this is a really fundamental statistical point that, frankly, many people involved, both the customers writing the contracts and the producers responding, often don't fully grasp. And that leads to significant, often unintended risks for everyone. And there's another layer here, too. It's subtle, but really important. While MTTF is common, especially if you assume a constant failure rate.
Which we'll come back to.
Right. But sometimes just knowing the MTTF is less informative than understanding how the failure rate changes over time. For lots of complex systems, especially mechanical or electromechanical ones, assuming a constant failure rate just isn't realistic. Things wear out, right?
Like that train axle bearing example you mentioned.
Exactly. It might fail early infant mortality, then have a long period of low, steady failures, but eventually wear out kicks in and the failure rate climbs. Just giving one MTTF number might completely miss that dynamic picture, which is why we often need more sophisticated tools like the Weibull distribution we can talk about. And we always have to remember, this idea of zero risk in these tests, it's a total myth. It's just not achievable in practice. Zero risk would mean testing forever or testing an infinite number of items. We can't do that. We don't have infinite time or infinite money. So acknowledging the risk, quantifying it, and then proactively managing it, that's absolutely fundamental. If you pretend the risk isn't there, you can't manage it. You're basically flying blind.
Absolutely. Flying blind is not where you want to be with critical systems. Okay, so if acknowledging risk is step one, then designing tests that actually manage that risk is step two. How do we get beyond those potentially misleading simple rules and design smarter, more reliable tests? Well, a really crucial concept here, one that basically measures how well a test can tell the difference between a good system and a bad one, is called the discrimination ratio.
A very important metric.
Let's unpack that a bit. Typically, you have a design target reliability. Let's call it R0. This is the reliability level you want the system to hit, the goal. Then there's a minimum acceptable reliability. Let's call that R1. This is the absolute lowest level you tolerate before saying, nope, this isn't good enough. Reject. The discrimination ratio is worked out based on the failure probabilities linked to R0 and R1. Basically, the higher this ratio is, the better your test is at clearly distinguishing between a product that genuinely hits the target, R0, and one that falls short, R1.
It's about making the dividing line sharp, not fuzzy.
Exactly. A higher ratio means your test is more sensitive, more precise, better at sorting the good from the not so good. Now, when it comes to actually designing these tests, these sampling plans, there are generally two main flavors. First, you've got what's called a two-sided sampling plan. This is often seen as the more comprehensive way to do it, the balanced approach. Here, you specify both the desired reliability, R0, and the minimum acceptable reliability, R1. And crucially, you also explicitly define and agree on both the producer's risk, alpha, that chance of rejecting a good product, and the consumer's risk, beta, the chance of accepting a bad one.
So both parties agree on the risks they're willing to take.
Precisely. With those four key parameters locked in R0, R1, alpha, and beta statistical methods, then help you figure out the smallest sample size, N, meaning how many units to test, and the maximum acceptable number of failures, C, that satisfy all those risk constraints. It aims for a calculated balance, protecting both sides fairly. It stops the producer from being unfairly penalized while making sure the consumer is adequately protected. Ideal when both sides have significant skin in the game, Then, sometimes you might use a one-sided sampling plan. This is simpler. Here, you only specify one reliability value and one type of error. The focus is mainly on protecting just one party. For example, a contract might be written purely to protect the consumer. So you set a minimum acceptable reliability, R1, and define the consumer's risk. The test is then designed to be really tough on accepting poor quality, maybe allowing for a higher producer's risk as the trade-off.
So it might reject some acceptable products, but it's very unlikely to accept a bad one.
It's exactly. Or, conversely, a producer might design a one-sided test mainly to minimize their risk of rejection, alpha, perhaps being willing to accept a slightly higher consumer's risk. It simplifies the design, yes, but it focuses protection on just one side. The choice really reflects where the main risk tolerance lies, or maybe who holds more power in the negotiation. And it definitely impacts how strict and how costly the test ends up being.
And this choice, this need for more sophisticated plans, leads us right back to handling the messy reality of how things actually fail. You see, that assumption of a constant failure rate. While it's convenient for math, and okay for some electronics, it's often just too simplistic for many real-world systems, especially mechanical stuff, electromechanical components. Think about it. A car tire doesn't fail at the same rate throughout its life, does it? It wears down.
Right. Obvious wear and tear.
And complex railway parts, they might have a high failure rate right at the start. Manufacturing defects, infant mortality, we call it. If they survive that early phase, yeah, they might settle into a nice long period with a low, fairly constant failure rate, their useful life. But then eventually, after enough use, enough cycles, wear out starts. Fatigue, degradation. And the failure rate starts climbing again, often dramatically. We often visualize this as the bathtub curve, right? High at the start, low in the middle, high again at the end.
The classic bathtub shape, yeah.
To capture that more realistic behavior, especially the changing failure rate, we often turn to the Weibull distribution. It's probably one of the most widely used models in reliability engineering, precisely because it's so flexible. It can model systems where the failure rate changes over time. It helps us model those early failures, the infant mortality and the wear-out effects later on, and lets us map that whole life cycle, not just assume a flat line.
Okay, so it's a more powerful, more realistic tool. How does it actually work in practice then? How do you use it to design a test?
Well, the key thing with Weibull is that it needs some a priori knowledge. You need an estimate of something called the shape parameter, usually denoted by beta. This beta value is incredibly informative. It tells you how the failure rate is changing. If beta equals 1, the failure rate is constant. That's the same as the simple exponential distribution assumption, useful for some electronics. If beta is less than 1, the failure rate is decreasing over time. That signals infant mortality, early defects getting weeded out. And if beta is greater than 1, the failure rate is increasing. That clearly signals wear out is dominant.
And where does this beta value come from? Guesswork.
Hopefully not guesswork. Ideally, it comes from historical data on similar products, or from accelerated life testing results. Sometimes even from physics of failure models, trying to predict how degradation mechanisms work. Once you have a reasonable estimate for beta, you then use specific Weibull formulas. These help you calculate things like the number of items you need to test or how long the test needs to run. You typically calculate another parameter called the scale parameter, eta, which relates to the characteristic life based on your target reliability and your beta. Then you use that to find the expected reliability for your planned test duration. And finally, that feeds into determining your sample size or required test time.
Okay, maybe an example would help make that clear, especially for our listeners interested in railways.
Sure, let's walk through a concrete railway component example. Imagine you need to demonstrate that a specific critical component, let's say a hydraulic damper for a train suspension system, has an MTTF, a mean time to failure, of 75 hours. And the requirement is strict. You need 95% confidence that 0 failures occur during a 60-hour test. So your acceptance number, C, is 0. Any failure means the test fails. Now let's also say you have good historical data, maybe from previous damper designs, suggesting this type of component follows a Weibull distribution with a shape parameter, beta, of 1.5.
Okay, so beta, it's 1.5. That's greater than 1, so that means wear out, right? Failure rate increases over time.
Exactly. Which makes sense for a mechanical damper subject to fatigue and wear. So step 1 is to calculate the Weibull scale parameter, A at A. Using the standard formulas relating MTTF, beta, and eta for the Weibull distribution, we plug in our target MTTF of 75 hours and our beta of 1.5. The calculation gives us an eta value of about 83.1 hours. Remember, eta isn't the MTTF itself, it's a characteristic life parameter that helps define the specific Weibull curve.
Got it. Eta is 83.1 hours. What's next?
Next, we need to figure out the expected reliability, or let's call it R hat, for our specific test duration of 60 hours, given our beta of 1.5 and the eta of 83.1 hours we just found. We plug these values into the Weibull reliability function. This function basically tells us the probability of an item surviving up to a certain time, 50. Doing that calculation, we find the expected reliability for a 60-hour test, R hat at 60 hours, is approximately 0.541, or about 54.1%.
So based on this model, there's roughly a 54% chance a single unit will survive the 60-hour test without failing.
That's right, statistically speaking. Now, the final step is to use this reliability value, 0.541, and our very strict condition of 0 allowed failures, C0 though, along with the required 95% confidence level to solve for the necessary sample size, etc. There are formulas for this too, often involving logarithms. When you crunch those numbers, it turns out you need to test approximately 4.88 units.
Can't test 0.88 of a damper.
No, you can't. So you always round up to the next whole number. In this case, you need to test 5 units, 5 dampers.
Okay, so test 5 units for 60 hours.
Mm-hmm.
And what's the catch?
The practical implication is really strict for the manufacturer. If even one single failure occurs among those 5 units during that 60-hour test, the entire test fails. They haven't demonstrated their required 75-hour MTTF at 95% confidence.
Wow. One failure and it's back to the drawing board, or facing penalties.
Pretty much. It really shows the rigor involved when you use models like Weibull, especially with high confidence and 0 failure requirements. It also highlights just how crucial getting that beta parameter right is. A small error in estimating beta could drastically change the required sample size or test time.
That's a fantastic, really clear example. It shows the detail and, frankly, the unforgiving nature of this kind of analysis. Okay, now let's pivot slightly and talk about something you called the cost of trust. Let's explore that through another railway case study, one that maybe relies on that simpler, potentially riskier assumption we mentioned earlier.
Right, the constant failure rate assumption.
Yeah, we touched on it. It's less general than Weibull's, sure, but it's still very widely used, isn't it? Especially for purely electronic systems.
It is. For electronics, after an initial burn-in period to weed out early failures, their failure rate can often be reasonably constant over their useful life. So the math simplifies a lot. You often end up using the Poisson distribution to model the number of failures occurring over a given time period. Poisson works well when events happen randomly, but at a constant average rate. It's often called a memoryless process. Past failures don't change the probability of future ones.
And because it's mathematically simpler, it's often the default.
Often, yes, due to simplicity and historical use. But as we'll see, that simplicity can hide dangers if it's not applied carefully or if the underlying assumption isn't really valid.
Okay, so let's dive into this real-world railway scenario. Imagine a big project upgrading a whole signaling network, maybe. There's a critical system involved, say a new centralized traffic control system, multi-million-dollar investment. And the contract has a very clear requirement. Its MTTF must be at least 100,000 hours. That's the target. The producer, the company supplying the system, has to demonstrate they've hit this target during a 1-year defect liability period, DLP, after installation. And the contract says any train delay over 10 minutes caused specifically by this system counts as a failure against that MTTF requirement. Seems clear enough, right?
On the surface, yes. A performance target, a time frame, a definition of failure looks reasonable.
But here's the critical part. The initial, often problematic test rule that frequently gets proposed in these kinds of contracts. It might simply state that during this 1-year DLP, The observed MTTF calculated as total operating time, which is 1 year, or 8,760 hours, divided by the number of observed failures. TK must be greater than or equal to 100,000 hours. Or alternatively, if 0 failures are observed during that year, the requirement is also considered met.
The classic observed MTTF equals target or 0 failures observed clause.
Exactly. That's the kind of simple rule that, as you hinted, can hide some pretty significant and potentially unequal risks for both sides, because it implicitly assumes that 1 year is long enough to really know what's going on.
And this is where we absolutely have to unpack the true probabilities involved. This is where the risks become incredibly real and that cost of trust idea becomes starkly clear. Let's analyze that rule. First, let's look at it from the consumer side, the railway operator footing the bill. Suppose the system the producer delivers truly has an MTTF of 100,000 hours. It perfectly meets the requirement. It's a genuinely good, robust product. What's the probability that the consumer will actually accept it under this simple rule? Observed MTTF equals 100K or 0 failures. We're looking at a 1-year observation, 8,760 hours. If the true MTTF is 100,000 hours, the expected number of failures in that year is 800, 760, 100,000 equals 0.0876, very low. Using the Poisson distribution to calculate the probability of observing 0 failures when the expected rate is 0.0876, it turns out to be surprisingly high, about 91.6%, let's say roughly 92%.
Wow, 92% chance of accepting it if it's actually good. That sounds pretty fair to the producer.
It does. It means if the producer delivers what was asked for, the consumer is highly likely to accept it based on this test. Now, flip it. What's the producer's risk here? If their system truly meets the 100,000-hour MTTF, what's the chance it gets rejected? Well, rejection happens if they observe 1 or more failures. Since the probability of 0 failures is about 92%, the probability of 1 or more failures is simply 1 minus that. So about 8%.
Only an 8% risk for the producer that their genuinely good system gets rejected by bad luck. That seems quite low. Maybe even an acceptable risk for them.
It might seem acceptable, yes. An 8% chance of hassle if you delivered the goods. But here's the kicker. This is where a savvy producer who understands these probabilities, perhaps better than the customer who wrote the spec, might see an opportunity to take a calculated risk to save a lot of money. Imagine the producer thinks, okay, I'm willing to accept, say, a 20% risk that my system gets rejected after the 1-year DLP. That's more risk than the 8% they'd face if they actually built the Undertale system, but maybe they see a cost benefit.
Okay, so they're willing to gamble a bit more on rejection.
Exactly. Now, we can work backward. If the producer accepts a 20% chance of rejection, which means they want an 80% chance of acceptance, what level of true MTTF could they design to and still hit that 80% acceptance probability under this simple rule? We need to find the true MTTF, let's call it MTTF true, such that the probability of observing 0 failures in 8,760 hours is 80%. Running the Poisson calculation backward. It turns out they could design a system with a true MTTF of only about 40,000 hours.
Wait, what? 40,000 hours?
Yeah.
That's less than half the requirement, 2.5 times lower?
Yes, you heard correctly. A system that is fundamentally 2.5 times less reliable than the stated 100,000-hour requirement, 40,000 versus 100,000, still has an 80% chance of being accepted by the consumer under the simple TM equals 100K or 0 failures in a year.
Rule. That is genuinely shocking. So the customer thinks they're buying and specifying this top-tier 100,000-hour reliability.
Yeah, they put it in the contract.
But the test rule itself, the one they probably thought was straightforward, creates this massive loophole that allows a significantly inferior product, a 40,000-hour one, to skate through 80% of the time.
That's exactly the implication. Because over just 1 year, the chance of observing 0 failures, even from a 40,000-hour MTTF system, is still surprisingly high, around 80%. The test period just isn't long enough to reliably differentiate between 40,000 and 100,000 hours based solely on observing 0 failures.
Wow, so is this mostly down to the consumer just not understanding the statistics when they write the contract? Or are producers sometimes actively, leveraging this?
It's likely often a combination, but frequently it stems from a lack of deep statistical insight on the part of the specifier. They rate what seems like a clear requirement, but don't fully analyze the statistical power of the demonstration test they've also specified. And the cost of trust here is enormous for the railway operator. They believe they secured a 100K MTTF system, paid for it, but they've likely received something far less reliable. Think about the lifetime cost. Over a typical 20-year life of such a system, a 40,000-hour MTTF implies potentially 2.5 times more failures than the 100,000-hour system they thought they bought.
Which means
For a major railway, that could mean hundreds of extra train delays per year, millions more in maintenance, repairs, operational disruption costs, and potentially a significantly higher exposure to safety incidents derived from those failures. Meanwhile, the producer, they potentially save significantly on design, development, component quality manufacturing by delivering a less robust system, yet they still had a very high probability of passing the contractual test and getting paid in full. It starkly illustrates that trade-off. The producer's risk appetite versus the cost savings they can get by under-designing relative to a poorly defined test requirement. It shows how the test design itself can end up dictating the actual reliability delivered, sometimes even more than the headline requirement does.
That is a truly eye-opening and, frankly, quite sobering example. It
Yeah.
makes the cost of trust incredibly tangible. Okay, so if we want to avoid these traps, move beyond these simple but dangerous rules and get a much clearer picture of how effective any given test plan actually is. How do we do that?
Well, a really powerful tool for visualizing and understanding a test plan's performance is using operating characteristic curves, or OC curves.
Operating characteristic curves. Okay, what are they showing us? Imagine a graph. It's a visual way to see how well a test plan does its job across a whole range of possible true reliability levels of the product being tested. On one axis, usually the horizontal one, you plot the true reliability of the system, maybe expressed as its actual MTTF, or perhaps as a ratio compared to the target MTTF. This represents the real underlying quality. On the other axis, the vertical one, you plot the probability that your specific test plan will accept a system with that true reliability level.
So probability of acceptance versus true quality.
Exactly. These OC curves map out that relationship. They let you see, at a glance, how likely your test is to accept or reject a product based on its actual inherent quality. And what these curves show you really clearly is that balance or imbalance between the producer's risk and the consumer's risk, right across the spectrum of possible true reliability values. An ideal OC curve, if you could achieve it instantly, would look like a step function.
Yeah.
It'd have a 100% probability of acceptance for all systems whose true reliability is at or above your target, R0. And then it would instantly drop to 0% probability of acceptance for anything below a minimum acceptable level, R1.
A perfectly sharp cutoff. Accept all the good, reject all the bad.
Precisely. But in the real world, with limited testing time and resources, you never get that perfect step. You get a curve. The steeper the curve is in that transition region between clearly good and clearly bad, the better the test's ability to discriminate. A shallow curve means there's a wide range of mediocre products that have a significant chance of being either accepted or rejected. Lots of uncertainty. And when you look at OC curves comparing different test plans, you see the trade-offs immediately. You mentioned some examples earlier, like maybe comparing a Plan B.5 versus a Plan B.8 from standard tables. Plan B.5 might show a much steeper curve. It stays very close to zero acceptance probability until the true MTTF gets really close to the target. It's very strict about rejecting anything less than ideal. It gives the consumer very strong protection, a low consumer's risk.
Low beta. But that protection comes at a cost.
Right. That superior discrimination, that steep curve, almost always means Plan B.5 requires a much longer test duration or a larger sample size, more time, more resources, more money spent on testing. In contrast, Plan B.8 might have a shallower curve. It allows for a quicker test, maybe fewer samples, saving time and money up front. But its curve might show a noticeably higher probability of accepting products, even when their true MTTF is significantly lower than the target.
So faster and cheaper, but riskier for the consumer. Higher beta.
Exactly. The OC curves graphically lay bare that fundamental tension. Test rigor versus risk versus duration and cost. They allow engineers and managers to look at these curves and make informed compromises based on what's most important for their specific project. Is it minimizing consumer risk at all costs, or is speed to market the absolute priority?
Absolutely. OC curves are indispensable for comparing test strategies. They really are the visual fingerprint of your risk profile. And speaking of comparing strategies, another really critical design choice comes down to the type of test plan structure you use. Broadly, we can compare time failure terminated tests, sometimes called fixed tests, versus truncated sequential tests. They both have their pros and cons.
Okay, let's break those down. Time or failure terminated first, the fixed ones.
Right. These are generally simpler to manage. You decide up front. Either you'll run the test for a fixed maximum amount of time, say 1,000 hours straight, or you'll run it until you observe a fixed maximum number of failures, say you stop after the third failure occurs. Whichever of those preset limits you hit first, the test stops, and you make your decision based on the results up to that point. Accept or reject, that's it. The test terminates.
What are the advantages there? Seems straightforward.
The main advantage is predictability. You know the absolute maximum test duration up front if it's time terminated, or the maximum number of failures you might need to deal with if failure terminated. This makes planning resources much easier. You can budget accurately for test rig time, lab space, personnel, energy, the number of test units you might consume. Scheduling becomes more certain.
Okay, predictable. What's the downside?
The downside is potential inefficiency. On average, these fixed tests can take longer to reach a decision compared to sequential tests, and they might accumulate more failures unnecessarily. Think about it. If the product is incredibly reliable, far better than the requirement, you still have to run the entire fixed time or wait for the maximum allowed failures, which might never happen. You can't stop early and declare victory.
Wasted time and resources, potentially.
Exactly. Conversely, if the product is really terrible, failing constantly right from the start, you might still have to continue the test up to the fixed limit, even though it's obvious early on that it's going to fail. Again, wasted effort.
Okay, so that's fixed test. What about the other kind? Truncated sequential tests. You said they're more dynamic.
Yes, much more dynamic, and often more efficient on average. With a sequential test, you don't just set one fixed endpoint. Instead, you continuously monitor the test results, the accumulated test time, and the number of failures observed so far. At various points during the test, you compare your current results against predefined statistical boundaries or criteria. Based on where your results fall, you make one of three decisions. 1, accept the product, enough evidence of high reliability. 2, reject the product, enough evidence of low reliability. Or 3, continue testing, not enough evidence yet to make a firm decision.
So you can potentially stop much earlier.
That's the main advantage. On average, sequential tests lead to an earlier decision. If the product is really good, it might hit the accept boundary very quickly, saving huge amounts of time and cost. If it's really bad, it might hit the reject boundary quickly, stopping you from wasting more resources on a doomed design. This efficiency, especially for very good or very bad items, is a major plus. Also, the total number of failures accumulated to reach a decision is generally lower with sequential tests, which can be a big cost saving if the test units themselves are expensive.
Sounds great. Faster on average, fewer failures.
Yeah.
What's the catch? Why the truncated part?
The catch. It's the predictability, or lack thereof. While the average duration is shorter, the maximum possible duration of a sequential test isn't fixed up front in the same way. If the product's true reliability happens to fall into a kind of statistical gray area, not clearly good, not clearly bad, the test might keep bouncing between the accept and reject boundaries without crossing either. It keeps telling you, continue testing.
So it could potentially drag on.
It could. That's where the truncation comes in. To prevent tests from running literally forever in these ambiguous cases, sequential plans always include a truncation rule. This is a predefined maximum time or maximum number of failures where the test must stop, and a decision, often based on which boundary was closer, is forced. But in these gray area scenarios, reaching that truncation point can sometimes take longer than a comparable fixed duration test would have taken. So while the average is better, the worst case duration can actually be longer, and it's uncertain beforehand. It depends entirely on the unknown true reliability of the thing you're testing.
So more uncertainty in the schedule.
Exactly. Uncertainty in the maximum timeline and resource planning, you gain average efficiency but lose some worst case predictability. Which brings us right back again to that core theme, trade-offs. Choosing between a fixed test plan and a sequential one is another crucial design decision. It really depends on your organization's priorities: risk tolerance, budget flexibility, schedule certainty versus average speed, and importantly, how much prior knowledge or confidence you have about the product's likely reliability. If you strongly suspect the product is excellent, a sequential test could save you a fortune. If schedule certainty is absolutely paramount for a market launch, a fixed test might be the safer, albeit potentially less efficient, choice. It's about designing the test as strategically as you design the product.
That makes perfect sense. It's all about informed choices and understanding those trade-offs. Okay, and that really wraps up our deep dive today into this crucial but maybe sometimes overlooked world of reliability demonstration tests. We've really unpacked why these tests are never, ever risk-free. We've seen those inherent producers and consumers' risks are just part of the game when you're trying to prove reliability for any complex system. We talked quite a bit about why those seemingly simple contract clauses can hide some pretty significant dangers, especially when they lean too heavily on rough estimates like TN for MTTF. That railway case study was particularly stark, wasn't it? Showing how a poorly constructed test could let genuinely under-designed products pass, massively increasing risk for the consumer that cost of trust made very real. But we also explored the smarter ways, the more sophisticated methods engineers have to manage these risks better. From understanding Weibull distributions to model real-world failure patterns, like that bathtub curve, to really weighing the pros and cons of fixed versus sequential test plans using tools like those OC curves. There are robust approaches to design tests that give a much truer picture of reliability and manage risk fairly.
And this whole discussion, this deep dive, for you listening, whether you're an engineering student just getting started, or maybe an early career professional finding your feet, or perhaps a seasoned railway safety enthusiast, it really isn't just about learning statistical methods. It's more fundamental than that. It's about responsible engineering. It's about due diligence. It's about building and maintaining trust. Every system you touch, design, build, operate, maintain, especially in critical areas like railways, it has an inherent reliability. And every test you run to try and measure or prove that reliability, it comes with a calculated, unavoidable risk. So maybe the takeaway is this. The next time you see a reliability requirement in a spec sheet or you're reviewing test results for a new component, don't just glance at the numbers. Don't just accept a simple pass or fail without digging a little deeper. Ask the questions. Ask yourself, what are the hidden risks baked into this demonstration test? What assumptions are being made here about failure rates, about test duration, about sample size? And are we genuinely optimizing for safety and for cost and for time in a way that builds real lasting trust? Trust not just in the component, but in the whole validation process behind it. Because at the end of the day, the reliability of our critical infrastructure, the safety and efficiency we depend on, it really hinges on how wisely, how thoughtfully we navigate these complex and often quite hidden risks.